Welcome! Do you know the shape electrical wires follow? It is not a parabola, as you might guess at first, but the so-called catenary, which is the graph of the hyperbolic cosine function. In this video, you will learn about this function and its cousins, the hyperbolic sine and tangent. The graph of the hyperbolic cosine is also used for arches, such as the Gateway Arch in St. Louis, as it transports the forces very well to the sides. The hyperbolic tangent is used to determine the probability that one player wins from another in chess, based on the difference in rating they have. The hyperbolic sine describes the shape of this soap film. The wire is the sine over half a period, and from this side the film shows the graph of the hyperbolic sine. In this video you will learn the basics of these hyperbolic functions and see why you should be interested in them. The definitions of the hyperbolic trigonometric functions are given in terms of the exponential function. The hyperbolic cosine is just e to the power x plus e to the power minus x over 2. The hyperbolic sine is the same with a negative sign, and the hyperbolic tangent is the quotient of the hyperbolic sine and the hyperbolic cosine, in similarity to the trigonometric functions. This means that any identity involving the hyperbolic functions can be rewritten in terms of exponentials, and the other way around. Determining whether to use exponentials or hyperbolic functions is thus often a question of taste, and involves deciding which give the simplest expressions for the problem at hand. The name hyperbolic function arises from the idea that their relation to a hyperbola is the same as that of a sine and cosine to a circle. The circle x squared plus y squared equals 1 can be parametrized as cosine of t, sine of t. This means that the points on the circle can be described as cosine t, sine t for certain values of t, the angle between the positive horizontal axis and the line to the point. The formula x squared minus y squared equals 1 defines a pair of hyperbolas. Notice the minus sign in the equation. The points on the right hyperbola of this pair can be parametrized as hyperbolic cosine t, hyperbolic sine t. So similar to the circle, but now with hyperbolic cosine and sine. You can easily check that points of this form are lying on the hyperbola by plugging in the expression for the hyperbolic trigonometric functions in terms of exponentials. Indeed, you can prove any identity in this video in a similar way. So what is the interpretation of t? Well, if you go back to the circle, you notice that the green area equals t over 2, as the surface of the entire disk equals pi, which is half the circumference. Similarly, in the hyperbolic case, t over 2 equals the green area indicated. Let us now consider the graphs. First, the hyperbolic cosine. It looks a bit like a parabola, but it is steeper. Indeed, the orange parabola does not grow as fast. Instead, the hyperbolic cosine increases exponentially as x goes to plus or minus infinity. For example, for very large x, the hyperbolic cosine looks very much like the green graph of e to the power x over 2. The hyperbolic sine is an odd function, which goes from minus infinity to plus infinity. It also grows exponentially on both sides. Finally, the graph of the hyperbolic tangent is an S-curve. It has the values minus 1 and 1 as horizontal asymptotes. As you can see, for very large x, both the hyperbolic cosine and sine look very much like e to the power x over 2. And thus their quotient, the hyperbolic tangent, will approximate 1. the trigonometric functions satisfy many nice relations. Long lists of double angle formulas and other formulas you don't want to remember. All these formulas have hyperbolic analogues. The ones shown here are just for illustration. Notice that sometimes a sign changes in these formulas, but for the rest they are quite similar. Because hyperbolic functions are defined using the exponential function, we can prove the right-hand formulas by just expanding the expressions in exponentials. This is much easier than the proofs of their trigonometric counterparts. Our motivation for considering these functions is their role in differential equations. Calculating the derivatives, we see that the hyperbolic functions once again look just like the regular cosine and sine. But notice there is no minus sign in the derivative of the hyperbolic cosine. These derivatives imply that differentiating twice returns the original function. In the trigonometric case, the second derivative of the cosine and sine is minus the original function. In the hyperbolic case, it is the original function itself. As these are second-order linear differential equations, and we know two independent solutions, we can now write down the general solution to these equations. But wait a minute, you already know a general solution to y double prime equals y. These are just e to the power x and e to the power minus x. However, recall that for y double prime equals minus y, we also had a solution in terms of exponential functions. In the trigonometric case, these were complex exponentials, and thus we do not want to use them. However, the functions e to the x and e to the minus x are nice and simple, so why consider a different way of writing these solutions? The reason the hyperbolic functions are nicer than the exponentials is related to the fact that they behave nicer with respect to certain initial value conditions. Indeed, consider the simplest example y of 0 equals 1 and its derivative equals 0. In terms of exponentials, the solution becomes 1/2 e to the power x minus e to the power minus x. Indeed, this is just the hyperbolic sign. And the alternative initial values where y prime of 0 equals 1 and y0 vanishes give the hyperbolic cosine as a solution. Thus, the hyperbolic functions are the ones which appear most naturally when you consider these initial value problems. Did you notice the little logo in the top left? That's a solution to the so-called Laplace equations, which involves the hyperbolic sign. Learn more about it in class.